Let's start by looking at what happens inside a wire. When we measure electric current, we are tracking the exact rate at which electric charge flows through a specific cross-section of a conductor over time. This image shows the mathematical definitions we use to track that flow. On the left, average current calculates the macroscopic change in charge over a set block of time. But if we shrink that time window down to an infinitely small slice, we get the instantaneous current, defined with calculus as I equals dq over dt. Looking at these notes, we see electric current is defined as a scalar quantity. Its standard SI unit is the ampere, but you will also see it measured in the CGS unit called the biot. Note the precise conversion factor here. 1 biot is equal to exactly 10 amperes. Moving to the text at the bottom, there is a strict convention for plotting the direction of this flow. Current is always drawn parallel to the motion of positive charges and directly opposite to the motion of negative charges. Grasping these directional rules and basic rate definitions gives us our baseline. We need this solid foundation before we can apply integration to evaluate complex electrical systems. Transitioning to integration, rearranging the current formula isolates dq. Taking the definite integral solves for total transported charge. As highlighted, this integral has a geometric equivalent. Total charge equals the area under a current versus time graph. For a special case where charge circulates continuously in an orbit, current is calculated using charge divided by time period. By factoring in orbital frequency and velocity, we map out these three sequential formulas. To apply integration, if current increases linearly as I equals 20 plus 3t, setting our definite integral boundaries from 0 to 10 finds total charge. The power rule yields 20t plus 3t squared over 2. Substituting 10 gives 350 coulombs. Whenever current fluctuates over time, basic algebraic multiplication fails to capture the changing rate. Integration and geometric area are the precise mathematical tools required to find the actual transported charge. Moving to a calculus optimization problem, we have a scenario where charge flow follows a given cubic equation over time. Our objective is calculating the minimum current value. Pause the video for a moment. Use your derivative rules to find the equation for current. Taking the first derivative of the charge equation yields instantaneous current. Setting its derivative to 0 solves for time t. Substituting this time into the current equation simplifies to produce the actual minimum current value, shown at the bottom right. Finding an absolute minimum requires disciplined mathematical execution. Knowing when an event happens requires completing the final substitution to calculate the exact value. This chart shows a triangular current time graph peaking at 10 amps over a 15-second duration. The challenge here is to determine the average current across this entire interval. The intuitive trap is to average the peak values or divide the maximum current by 2. Calculating average current over a varied curve requires finding the total accumulated charge first. Looking at the bottom left calculation, we find that total charge by calculating the geometric area of the triangle. Multiplying 1/2 the base of 15 seconds by the height of 10 amps gives us a total charge of 75 coulombs. Now we take that total calculated charge of 75 coulombs and divide it by the total time interval of 15 seconds. This final step reveals that the true average current is exactly 5 amps. Let's lock in these core calculation methods. They rely on 3 distinct pillars. First, the calculus rate definitions. Second, integration and graphical area. And third, formulas for circular motion. Mastering current electricity requires translating between these forms. Once you can accurately move between geometric area, calculus rate equations, and physical charge totals, you can evaluate the precise behavior of any electrical system.